Hello, and welcome back to AP Environmental Science. Today, I want to talk about the flow of matter through ecosystems, and in that respect, we'll be talking about the biogeochemical cycles. Now, in our class, we will talk about the flow of matter, and we will also talk about the flow of energy when we talk about trophic levels and things like that. And we want to talk about the difference between matter and energy, and that is going to be a little bit of a review because probably you've discussed this in another class at some point. But just to start a review, matter is anything that has mass and takes up space, anything solid, anything that gives off energy, or all of the choices. Well, it's really anything that has mass and takes up space. It does not have to be solid, right? Because we've got gases and liquids and plasma. It does not actually have to give off energy, although most matter does. I mean, think about you. You give off lots of energy because you're an endotherm. But it doesn't have to give off energy. That would be the definition of a black body, for instance. Carbon, things like that, which you've probably talked about in physics, so we won't talk about that. But anything that has mass and takes up space. All right, so from there we can remember the rules, which are that matter can neither be created nor destroyed. That is the law of conservation of matter, although it does not actually apply on the nuclear level. So for those of you that have done some quantum stuff, it's a little questionable there. It can be changed from one form into another, right, within that same rule about not being created or destroyed, and it can be recycled, right? So it can be used over and over and over again. All right, so let's talk a little bit about organic compounds, because when we talk about biogeochemical cycles, we'll be talking about elements that are involved in organic compounds and inorganic compounds, and then we'll also at some point be talking about organic and what it means actually in your life, because you hear the term organic a lot. So we want to start looking at the sort of levels of definition of that. But an organic compound is what? Something that's not treated with artificial pesticides, contains only carbon, is found in only living organisms, contains carbons linked chemically to hydrogen or other carbons, or are organic compounds those only found in solid form. Well, organic compounds are found in living organisms, but they're found in other things too. Basically, what we're talking about is we're not just talking about carbon compounds, we're talking about carbon and hydrogen compounds, hydrocarbons. Those are the organic things. Anything that is carbon and hydrogen, there can be other stuff in it too, but as long as it's got carbon and hydrogen, it's an organic compound. So some examples of that would be glucose, right? Methane, carbon-based molecules, but they've got to have hydrogen. So inorganic would be something that is not carbon and hydrogen. So here's my question to you though. What about carbon dioxide? Carbon dioxide has carbon, but it doesn't have hydrogen. So carbon dioxide is not organic. It is inorganic because it's lacking that hydrogen. All right, so now on to the next kind of idea that's also a review. What about the elements of life? There are 92 naturally occurring elements, and there are lots and lots and lots of ways that you can pair those elements up together or match them up, not just in pairs, right? But when we talk about the elements found in living organisms, there are a bunch of them, but there are some that are definitely in greater quantities. I mean, think about carbon, right? Living things are made of hydrocarbons. So carbon is one of them. Hydrogen, oxygen, those are big ones. Phosphorus, potassium, right? And you can see here, I'm not going to read all of these, right? Now, in some of these are all kind of the big things. The first one, C. hopkins, those are the ones that are in the greatest amount, right? And I'll just finish off those. I stopped at potassium, then we've got iodine, nitrogen, and sulfur. Now, the rest of them, the calcium and iron and all of that, those are our metals, right? Except boron. But those are our metals, and they are going to be in much smaller quantities. Okay, so we're going to divide these things up into two categories. We've got the macronutrients. Those are the really big quantities, right? And I like to remember those with the acronym INCHOPS. And so you can remember it that way. And INCHOPS is actually the 5 biogeochemical cycles that we talk about. So the first one here, we've got nitrogen and carbon, and then we've got water, and then we have phosphorus and sulfur. Now we've already talked about the water cycle, but we will be talking about the other 4 today. We will concentrate more heavily throughout the course on the nitrogen and carbon cycles, but you do need to also know the phosphorus and sulfur cycles as well. Now these are all really great elements. Yay, right? Think about, as we're going through the course, what are some elements that might be harmful to living organisms, right? Whereas iron, you want that. Do you want lead? That's another metal, right? But it turns out that lead is poisonous. So I want you to think about how that works. What's good? What's bad? What about things that are good in small quantities, but they're bad in large quantities? And we'll be kind of focusing on that in terms of exposure and limits, right? Maximum contaminant levels and things like that. All right, so moving on to the biogeochemical cycles, let's talk a little bit about nature, who's the original recycler. So ultimately what we have is we have the abiotic components and we have the biotic components of the ecosystem. The abiotic components are going to be the atmosphere, the hydrosphere, and the geosphere portion, right? That's going to be the soil and the sediments and all of that. Then we have the biosphere, and that will be all of the living organisms and their products. So let's start with the carbon cycle. And we've talked a little bit about the carbon cycle before when we've talked about water and we've talked about CO2 dissolving into the ocean and how the ocean is a carbon sink and things like that. But when we put the whole carbon cycle together, we know that there is CO2 in the atmosphere. And there are other things in the atmosphere too. There's carbon monoxide, there's methane, right? Those things are released naturally. CO2 is released by animals. It's released through decomposition. Then we've got methane, which is released through decomposition as well. It's also decomposition. And then we've got carbon monoxide, which can come from various things, can also come from volcanic eruptions. So there's all sorts of natural components here. We know that the CO2 is taken up by plants and then they release oxygen. That's locked up into organic molecules beginning with glucose, and then it's used to build tissues, and so you get lots of things. When we get that CO2 in the ocean, we get carbonate, which was the CO3 polyatomic ion, and that will bind with calcium to make calcium carbonate, which is what little animals make shells out of. So we've talked a little bit about a bunch of this stuff before. We'll talk about it in great detail when we talk about the atmospheric content and global climate change. But just to give you an idea, this is sort of an overview of the carbon cycle. Now, it turns out that carbon can be found as a solid, a liquid, and a gas as it moves through the cycle. So which of the following laws would explain this? Well, you already know the answer to it. It's the law of conservation of matter. We already talked about this, that things can change form, but they can't be created or destroyed. The second 2 things on the slide, the laws of thermodynamics, refer to energy flow, and we will talk about that when we talk about energy transfer in ecosystems. Now, I put this in here just so you can see some more about the flows of carbon, and then a little bit about how much in, say, gigatons of carbon per year that we're getting on average in transferring between the various reservoirs of carbon. Everything in red is human oriented, and we'll talk about that more later on. I also put this slide in here to show you those exchange cycles. Where are you getting kind of these constant cycles that are within the system, but they're sort of like tiny little loops in that system. Okay, so take a look at this at some point. All right, so now one of the things that we really want to do as we're talking about these cycles is we don't just want to identify the natural parts of the cycles, we want to identify our effects on these cycles. And ultimately, our biggest effect on the carbon cycle is that we add excess CO2 to the atmosphere by burning fossil fuels and by clearing vegetation faster than it's replaced. Now, the thing about that is that we remove that sink of forests and the decomposition of those plants, and oftentimes we burn down forests to make room for agriculture. That adds CO2. Both the decomposition of the plants and burning them adds more CO2. So you get kind of a double hit on the whole deforestation thing. All right, let's talk about the nitrogen cycle. The nitrogen cycle is going to be mostly in living things, right? When we were talking about the carbon cycle, we have lots of different forms. We've got the methane, the carbon monoxide, the carbon dioxide, calcium carbonate, carbonate, right? Bicarbonate, all that good stuff. Having said that, oh, and then we'll talk about VOCs, which are volatile organic compounds. A lot of those are lots of carbon. So carbon takes lots and lots of forms throughout its cycle, right? And it's in lots of different reservoirs. It's in inorganic states and organic states because of the whole carbon thing. Nitrogen is going to be mostly cycling through the biosphere. Now, there's a lot of it in the atmosphere, right? There's a lot of atmospheric nitrogen. 78% of the atmosphere is in fact nitrogen gas. Nitrogen gas is completely unusable to the living systems, right? So what has to happen is you have to have some sort of facilitator to turn that atmospheric nitrogen into something that is usable by plants, and that facilitator is bacteria. So here's the thing that's special about the nitrogen cycle. The nitrogen cycle is dominated by bacteria. It is driven by bacteria. Okay, so what happens is you have atmospheric nitrogen, it is fixed, and this is called nitrogen fixation, and I have put for you a summary of all of the steps of the nitrogen cycle on our learning management system, and so you can find that under the day for biogeochemical cycles. And so you definitely want to check that out. But nitrogen fixation is going to be the first step, and nitrogen fixation is occurring by bacteria, right? And they are going to fix that nitrogen to a hydrogen. A lot of the nitrogen fixing bacteria live in the soil, but there are some that actually live in nodules in roots. And so when you look at this, you can actually see these little nodules in here. That is where bacteria live in the plant, and those actually help those plants get the nitrogen that they need, because remember, nitrogen is really important in terms of living systems, right? Okay, so whether you're talking about your bacteria living in root nodules or you're talking about just soil, they will turn that nitrogen gas into ammonium, right? Ammonium is NH4+. It is a really good thing. Okay, we like that. It's exciting. It's part of fertilizer. Plants love it. Okay. Ammonification. So I want you to remember ammonium. It's ammonium-y for plants, right? Now, the next set of bacteria are your nitrifying bacteria. Okay, they're your nitrifying bacteria. Nitrifying bacteria, there are two different kinds, and they will go through a two-step process. The first type of nitrifying bacteria will take that ammonium, and it will turn it into nitrite. Now, nitrite is toxic. It is not right, nitrite, not right. For plants, right, it's not right for plants. So nitrites, they will be toxic for plants. It's not good. The next set of nitrifying bacteria, they happen to like nitrite a lot, but they will produce nitrate. And nitrate is good. Ammonium nitrate, as a matter of fact, is a really good fertilizer. Also happens to be explosive, but it's a really good fertilizer. Nitrates can be assimilated into plant roots, right? Nitrates can be assimilated in plant roots, and this is really helpful. Okay, nitrate is a really good thing. So ammonium and nitrate, really good. Nitrite and ammonia are toxic. Ammonia is a waste product of animals, and that ammonia has to be converted into something that is not toxic. Okay, so we assimilate in plants. The plants are eaten by animals. The animals produce waste. The animals decompose, and that's going to release nitrogen. So that ammonia and all of the decomposition waste is going to be undergo ammonification again, and it will be turned into ammonium, and then you can have the nitrification process, and then assimilation, which is the taking up through the roots. Okay, now some nitrate is denitrified, which means it's turned back into, it's turned back into nitrogen gas in the atmosphere. So while most of the cycle is going to deal with soil and living things, you have the nitrogen fixation from the atmosphere, and you have the denitrification that returns atmospheric nitrogen to the atmosphere. okay, or nitrogen gas to the atmosphere. All right, and that is an overview of the nitrogen cycle. Please make sure that you look at those steps, okay? And here is your next question. So, which of the following process converts nitrogen in the soil back into a gas in the atmosphere? Well, we know that fixation is going to capture atmospheric nitrogen. It's going to turn it into ammonium, and then we're going to go through that nitrification process. We're going to get up into living systems, and then nitrate can be converted by bacteria through denitrification, step 3, back into nitrogen gas, and then we'll go into the atmosphere. All right, now I put this in here just so you can kind of connect the nitrogen cycle to eutrophication, right? Aerobic conditions and anaerobic conditions, what happens? Nitrate will, in anaerobic conditions, often be reduced by those denitrifying bacteria to go back to be nitrogen gas. And then in aerobic conditions, you can see very much that ammonia, ammonium, nitrite, nitrate cycle, right? So just to give you an idea of like how that works in water. Anyway, all right, what are the effects of human activities on the nitrogen cycle? Oh my goodness, we have so many effects on the nitrogen cycle. We add nitrogen and a variety of NOxes to the atmosphere by burning fossil fuels, through deforestation, through industrial processes, through agriculture. We also add lots of fertilizer, right? Just in general, it gets into waterways, it results in eutrophication. And so what we're seeing as we have all of these impacts is we put all of this extra, we put lots of nitrogen out there. We're getting more acid rain. It can contribute to global climate change, and it contributes to ozone formation, which we talk about when we talk about ozone and air pollution. All right, let's talk about the phosphorus cycle. The phosphorus cycle is really simple, okay? Phosphorus really exists as phosphate. So in the other cycles, you've got to remember all these different chemical forms and all of these transitions, these processes. For phosphorus, you have phosphate in organic compounds, right? Phosphate is a fertilizer as well. It is taken up, it is assimilated by plants, it's eaten by animals. Those animals poop. Let's just be honest, they die, right? And so it gets back into the soil through decomposition, either of the waste or of the animals themselves. In the soil, it can get locked up in rocks. It can bind with metals to form compounds. So you get all sorts of things. Most of the phosphate is actually locked up in rock. And so this is a really big reservoir. It's dissolved in water. So you've just got this very basic cycle. It's released through weathering and decomposition. There is no phosphate in the atmosphere. It's too heavy. It's actually too heavy to be in the atmosphere. Which brings me to the next question. How is the carbon cycle like the nitrogen cycle but different from the phosphorus cycle? Nutrients are passed from one trophic level to the next. There's a large reservoir of the element in the atmosphere. Plants are able to incorporate the element directly from its atmospheric form into plant compounds. Bacteria are involved in converting one chemical form of the substance to another. It's formed naturally due to the breakdown of sedimentary rocks. Well, nutrients are passed from one trophic level to the next, right? Stuff eats stuff and they get stuff. And that's going to be true for all of our macro and micronutrients. So that's not it. There is a large reservoir of carbon in the atmosphere. There is a large reservoir of nitrogen in the atmosphere, and there's way more nitrogen than carbon, but that's true, it's all in the atmosphere. There is no phosphorus in the atmosphere, so 2 is the answer, right? But let's just go ahead and address 3, 4, and 5. Plants are able to incorporate the element directly from its atmospheric form into plant compounds for none of these things, right? Well, that's not true. In the atmosphere, carbon dioxide is, right, taken up by plants. It is taken up by plants, but nitrogen gas is not taken up by plants, and phosphorus is not in the atmosphere at all. Bacteria That's in the nitrogen cycle, not the carbon cycle, not the phosphorus cycle. Now, are bacteria involved in the carbon cycle and the phosphorus cycle? Sure they are, right? Because decomposition, right? It's bacteria that are going to be those big decomposers. Carbon is not formed naturally due to the breakdown of sedimentary rocks. That is a phosphorus thing, okay? All right, so how do we affect the phosphorus cycle? We actually use lots of phosphate to make fertilizers. Okay, most of your fertilizers have a lot of phosphate in them, and we get that from phosphate-rich rocks that we mine and quarry. We also reduce phosphorus in tropical soils by clearing forests. Okay, phosphate available in the soil in forests. Tropical forests particularly is real limited, right? Because in tropical forests you have lots of cycling of nutrients very, very quickly, and they are mostly locked up in the massive amounts of organic material in the biosphere. And so tropical soils are really nutrient poor. They're really, really nutrient poor. And so when we take away the trees and stuff, we actually take away the phosphate. Now, we also add excess phosphates through all that fertilizer, through runoff of animal waste, and from detergents. Phosphate is a major component in detergents, right? Now, all of this results in phosphate in the aquatic system, and we know that phosphate is a nutrient and it leads to eutrophication. So we actually are really heavily impacting the phosphorus cycle, which is an interesting thing because phosphorus is actually usually the limiting resource. Phosphorus is usually the limiting resource in all ecosystems. This is the one that you're going to run out of first. And so it's a very kind of tight cycle. So when we affect it, it's kind of a big deal. So this is just the phosphorus cycle again, but in it has been added these pathways from humans, and here's another version of it just so you can kind of get sort of multiple slides that'll give you a complete picture. All right, which of the following is not true about the phosphorus cycle? It has both natural and human influence steps. The natural source of phosphorus is the breakdown of rocks and soil. Phosphorus can be fixed naturally by soil-dwelling bacteria. Because phosphorus is formed slowly, it's often a limiting nutrient in natural ecosystems. And when agricultural phosphorus leaches into water, algae and phytoplankton populations can grow, very quickly. Well, like all the cycles, it has natural and human influence steps. We already know that the natural source of phosphorus comes from rocks, right? Phosphates released from the rocks as they weather. We know that the phosphate, right, is formed slowly, it's released slowly, so it's a limiting nutrient. We know that when we release fertilizer into the water, we get eutrophication. But remember, there's no phosphorus-fixing soil-dwelling bacteria. That is a nitrogen cycle thing. Okay, last cycle is the sulfur cycle, and we will spend less time on the sulfur cycle than the other cycles probably. It doesn't make it any less important. It's just that it's... Well, that's not true. We'll spend as much time on this as we will anything else. Okay. Remember, though, our big focus is on the nitrogen-carbon cycle. Phosphorus and sulfur are secondary. Sulfur is one of those that has lots of different forms. You're going to see it in sulfate. You're going to see it as sulfur dioxide, sulfur trioxide, elemental sulfur, hydrogen sulfide. So here is just kind of an overview of the natural cycle. It's very much in a lot of ways like the carbon cycle. It's just that you're dealing with sulfur compounds. One of and you can see it. You're getting carbon monoxide and carbon dioxide out of volcanoes. Here you're getting sulfur dioxide and sulfate out of volcanoes. It's going to go in the atmosphere. You have sulfur oxides in the atmosphere. You have hydrogen sulfide, which is kind of in that same vein as methane. That's reduced sulfide. You've got it locked up in rocks in terms of gypsum and pyrite, whereas we see the carbon in calcium carbonate in rocks. So there's a lot of parallels between the carbon cycle and the sulfur cycle. So that's good in the idea that you've got, oh, this kind of predictable. It's bad in that it's a little bit easy to get confused, so don't. right? Now, like the nitrogen cycle, we do have sulfur-reducing bacteria involved. That's exciting, and that's true for all of the cycles in decomposition, right? Sulfate is the best form for plants to take up. Okay, so that's kind of a summary. Here is another slide. What I like about this slide and what you will like about this slide is it has the actual chemical forms that are involved in all of those areas that we just talked about. And I have put in an aquatic version so you can kind of see what happens in aerobic conditions, what happens in anaerobic conditions. All right, now how do we affect the sulfur cycle? We add a lot of sulfur dioxide to the atmosphere through burning coal and oil, not natural gas, but definitely coal, high in sulfur. Coal has lots and lots of sulfur. We refine sulfur-containing petroleum, and so we have all this excess sulfur that we've got to take out of it before we can use it. And then there's still some in it, which we burn. We also convert sulfur-containing metallic ores, right? There's a lot of metal sulfides, and we want the metal, like copper, lead, and zinc, but we don't want the sulfur. And so when we process that out, it releases a lot of sulfur dioxide into the environment. And so sulfur dioxide into the atmosphere actually forms sulfuric acid, and I will show you that in just a second. Okay, here is related to kind of agriculture when you have the sulfur. So this is just another slide to kind of tell you, but it focuses specifically on agriculture because there's sulfur in fertilizers too. And then here we can add in that human component, right? The pathways affected by humans. And I want to highlight over here the sulfuric acid component. And when we put all that sulfur dioxide from mining, from burning coal, from refining fossil fuels, from industrial processes, when we do this, it's actually going to form sulfuric acid from the water droplets, right? So the sulfur dioxide and water droplets mix, the hydrogen there's dissociated hydrogen in those water droplets, and that forms sulfuric acid, which is H2SO4, H2SO4 in the atmosphere, and that's how you get acid rain. It also turns out that sulfur dioxide will form sulfate, which can be, right, so that's part of that. You can also dry deposit that sulfate as well, but most of the time what you're going to get is wet deposition, which is acid precipitation. Now the other thing about this slide is it shows you there's one more form of sulfur, which is called DMS, dimethyl sulfide, and this is a bacterial byproduct of sulfur being dealt with in ocean sediments. This is kind of a unique thing in the sulfur cycle. You don't really see this step like in the carbon cycle or nitrogen cycle. Okay, so I know we did a lot of information today. I have 2 more mini quiz questions for you and then we will be done. A lot of information. Please make sure that you ask questions if you have them, but you need to have you need to have an understanding of these cycles. Okay, which 2 elements contribute to acid deposition or acid rain? Is it nitrogen and sulfur, nitrogen and phosphorus, phosphorus and sulfur, or phosphorus and carbon? Now this is an interesting question because all these things can form acid. You have nitric acid, you have sulfuric acid, you have phosphoric acid, and you have carbonic acid. We know that CO2 in the oceans forms carbonic acid, but you need to think about whether it does in the atmosphere or not. Well, remember, in the phosphorus cycle, we've locked everything up in phosphate. We don't get phosphorus into the atmosphere, and so we cannot have phosphoric acid in the atmosphere. So you cannot have phosphoric acid in acid rain because it's not in the atmosphere. Carbon only forms carbonic acid in the ocean, right? In water, like actually in water, not in the atmosphere. In the atmosphere, it stays as CO2. Nitrogen and sulfur, however, will form nitric acid and sulfuric acid, and they both contribute to acid rain. And then here is your last question. Which of the following effects do humans have upon nutrient cycles in natural ecosystems? Eliminating forests increase atmospheric carbon and reduce the ability of nature to take it up. Mining phosphorus has reintroduced stored phosphate into the phosphorus cycle. Artificial fertilizers have increased runoff into aquatic systems. Application of artificial fertilizers reduce the numbers and types of soil-dwelling nitrogen bacteria. Or we're decreasing the amount of each element in the cycle. That should say cycles. Well, 1 through 4 are true. We don't decrease the amount of each element in the cycle. You can't do that. That goes back to the law of conservation of matter. You cannot destroy or create matter. So all of the elements are still in the cycle, right? We just change where those elements are and what they're doing. But all 4 of these things are true. Oh, sorry. The question should say, which of the following effects do humans not have upon nutrient cycles in natural ecosystems? Which effect do humans not have upon nutrient cycles in natural ecosystems? And so the answer is 5. All right. Thanks for listening. Please make sure that you ask questions in class, and I will see you next time.